Hi everyone, it's really great to be here. What an honor to be doing a talk for the Royal Institution. Today I'm going to be talking about solar system science from the JWST. So Lisa already said a little bit about me, but I'll start with a little bit more. So as you can probably tell from my accent, I'm a fellow Brit. I grew up just outside of Newbury in Berkshire. I did my 4-year integrated master's in physics with astrophysics at the University of Leicester, graduated in 2012 and took a break for 5 years. Then I ended up back in Leicester for my PhD that I finished in September last year. And my thesis was looking at the atmospheres of the ice giants Uranus and Neptune. So a lot of this talk is going to be talking about those planets because they're my favorite. And I did that using the Spitzer Space Telescope infrared spectrometer, which I'll also talk about. And that's why I'm now involved with the JWST, because as I'll explain later, the ice giants are some of the most interesting solar system science targets for the JWST. And so I moved out to Maryland in October last year, and now I work at NASA Goddard Space Flight Center, employed by Howard University. I'm going to start by explaining what the JWST is. Then I'll outline its general use for solar system science. I'll talk about those solar system GTO programs, and GTO is guaranteed time observations. I'll explain a little bit about what that is when we get to it. And then I'll go into a bit more detail about how the JWST is going to advance ice giant science. And then I'll update you on where the JWST is now. And this talk is obviously very serendipitous that it's happened on the 12th of July, the day today when the first images were released just this morning, the afternoon for you guys. So yeah, very exciting times. So let's start with what is the JWST and why is it so special? So the JWST is an orbiting infrared observatory. It has a 6.5 meter primary mirror made of 18 separate movable segments. It has 4 scientific instruments that are housed at the back of the mirror and a tennis court sized 5-layer sun shield. And all of that was stuffed into a rocket launched into space, and then it slowly unfolded itself as it approached its home 1.5 million kilometers away, or 1 million miles away. And it's the premier observatory of the next decade. It's going to be serving thousands of astronomers worldwide. And this past 6 months, I've never in my life seen scientists this visibly excited. They're almost giddy about something. I've never seen this before. So it's a very exciting time to be a space telescope scientist. And building it has been an international collaboration between NASA here in the US, the European Space Agency, including the UK, and the Canadian Space Agency. So the main job of any telescope is to look at distant objects. It's gather light from those objects and focus it either into your eye, like a telescope you would have at home, or into an instrument or multiple instruments if it's bigger. JWST is unique because it's the first ever space telescope with movable mirror segments, and they need to be movable so that we could fold the telescope for launch, and also so we can adjust the focus remotely at any time, so we never run into the problems that happened with Hubble where we're out of focus and have to fix it. So each segment can be moved independently from one another to manually focus the light into the central detector and back into those instruments. And we'll get to each of those 4 instruments later on. The easiest way to explain the JWST is to directly compare it to the world's favorite space telescope, probably the world's second favorite space telescope now that JWST is up there, and that's Hubble. Hubble was launched in 1990. It celebrated 30 years in 2020, and it's actually the same age as me, almost exactly, which is exciting. And over 1.5 million observations have happened since it launched. And it produces beautiful images. These are examples here that I'm showing of amazing, groundbreaking solar system science that it's done. So it's observed everything from Mars all the way out to Neptune and moons and even more. Some of its biggest discoveries include finding 5 new moons of Pluto, observing multiple impacts at Jupiter, So imagine what JWST can do with even better technology. So how is the JWST better than Hubble? For telescopes, it's always bigger equals better. And this animation shows the relative size of both of those telescopes, and a larger mirror on the JWST, so that 6.5 meter mirror means there's more collecting area for light, so we can look at dimmer, smaller, colder, more distant objects than a Hubble with its 2.4 meter mirror. And that person down there for scale in the video shows the immensity of both of these observatories. They're huge. And a major difference, another major difference is that it's in the infrared rather than the visible that Hubble is mostly in. Visible light, what we can see with our own eyes, is what Hubble mostly sees. And when we split light up using a prism into a rainbow, towards the violet end, we stop being able to see light and get UV. And that's also a range that Hubble can see. And towards the red end, we again stop seeing light, but start to be able to feel it as heat instead of light, and that's called the infrared. And so JWST looks at heat like we look at light. And it sees in the near infrared. Hubble can see a little bit of the near infrared as well, but it also sees in the mid infrared, which Hubble can't see. And infrared is useful for scientists for many reasons. So the video here sees a nebula, so lots of dust and gas in space from Hubble. So first invisible, then we change to infrared, and we can look through that cold dust to see those hot stars forming inside. And for solar system science as well, it's also useful because we can use it to look at clouds and beneath hazes to see what's happening underneath, like on Jupiter. In this image from ESO, the left is visible and the right is in the mid-infrared. So because we're looking at heat, infrared, the instrument, the whole observatory needs to be kept cold. And Earth is extremely warm, so we need to go much further away than Hubble. And it's also why we need that huge sun shield. That sun shield, the big silver thing that's 5 layers thick, that is the size of a tennis court. So that's all for keeping the telescope as cold as possible. And that's a reason why we have it so far away. We have it at the L2 Lagrange point, which is 1.5 million kilometers away. And that's the Hubble is only 570 kilometers away in an Earth orbit. And a Lagrangian point isn't as complicated as it sounds. It's just a gravity well where spacecraft can kind of hover easily without using too much fuel and stay in constant communication with Earth as we travel around the sun. So it stays with Earth as we travel. And it uses less fuel to stay where we want it when it's in this gravity well. And there's a downside, obviously, to it being further away. Since the Hubble launch, there's been 5 shuttle missions to carry out repairs and upgrades on the telescope, and there's no way to do that for JWST. And that was a scary prospect for engineers, but most of those scary parts are over now. And for the JWST mission, we're pretty set and everything's working. And I'll talk a bit about what we're doing to ensure that it's ready later. So there are 4 instruments aboard, all housed in the ISIM, or the Integrated Science Instrument Module. That's the big box behind the mirror. And that includes the near-infrared camera, or NIRCam, the near-infrared spectrograph, or NIRSpec, the mid-infrared instrument MIRI, and the fine guidance sensor, or the FGS, which is otherwise called NIRIS, or the near-infrared imager and slitless spectrograph. And these instruments provide imaging and spectroscopic capabilities across the whole spectral range, so from the near-infrared all the way through to the mid-infrared. So what was it built for? JWST has 4 major science themes, and I usually show these like stock examples to explain this, but now we actually have real images I can show you that were released today, which is extremely exciting. And this is the first time I've got to show them off myself. And so, these first science quality images, or the early release observations, ERO, were released today and also a little bit yesterday by President Biden. And these first images were selected because they highlight these 4 science themes that inspired the mission. So let's start as far out as we can possibly get. So this image highlights objective 1, which is the first light objective. So we're looking back in time to see those first stars and galaxies forming in the early universe. And the universe is less than 13.8 billion years old. And the things that we're looking at here are up to 13.5 billion years old. So we're looking right at the start of the universe when it was first born. And this is a SMACS 0723, which is a galaxy cluster. And this galaxy cluster, the fuzzy things right in the center of that image, like the fuzzy white thing. And that is interesting for us because it bends the light around it and creates a gravitational lens. And so we're using the best artificial telescope, JWST, to look through nature's best telescope, which is SMACS 0723, and we can use this gravitational lens to look even further and deeper into the universe. And so you can see that lensing happening in the image and the mirroring of different galaxies in the image. So that's all of those stretched out, weird looking galaxies. They're kind of, if you look through a glass, you can see those kinds of strange distortions. And the galaxies here are all more than 13 billion light years away, meaning they're 13 billion years old. And this image was made amazingly in less than 12.5 hours of exposure time. And that's a very small amount for telescopes. To put it into context, this image in the right that I've provided from Hubble of the same object, the same galaxy field, took 10 days of exposure time to make. And it's not even anywhere near as good as the 12.5-hour exposure that we have here. So imagine what we'll see in the future when we start doing these 10-day exposures and how far we can look into the universe. We haven't even begun yet. Then if we come a bit closer to home, so I'm going to start coming closer and closer to Earth, we have Stefan's quintet. This is a visual grouping of 5 galaxies, of which 4 form the first compact galaxy group ever discovered. So this picture is actually 150 megapixels, so you can really zoom in on it. It's really fun if you find the big image that's on the NASA website. And it's made of 6 NIRCam tiles, all kind of stacked together to get this amazing quality. And the left galaxy in this image is a lot closer than the others at around 40 million light years away. So that's why each star you can see is resolved in the galaxy. And when you zoom in, you can really see each star in this galaxy, which is just amazing considering it's 40 million light years away. And then the other 4 galaxies on the right are around 290 million light years away. And they're physically interacting with one another. And that helps us with objective 2 to understand how galaxies assemble over billions of years. So some of these galaxies are actually colliding with each other, which is really exciting. You can see some of the dust and gas being heated up through that process. So let's come even closer to home. We can see through dust to look at where stars and planetary systems are being born to help with objective 3, which is the birth of stars and protoplanetary systems. And NGC 3324 is a star-forming region inside the Carina Nebula. And this is the real beauty of the announcement today. It's 9,100 light years away from Earth. And the Hubble image in the right is as good as Hubble can do. And this is just the beginning of what Webb can do in this image. It's absolutely beautiful. As soon as this is over, I'm setting it as my desktop background. And then this is the Southern Ring Nebula. It's also a planetary nebula. So gas has been thrown off by a red giant at the end of its life. And it's in the constellation Vela, which is about 2,000 light years away. And the left image here is in the near infrared by NIRCam. And the right image is from MIRI in the mid infrared. And this shows slightly different things for each wavelength range. We'll see this in solar system science as well. And it's so detailed in that near-infrared image that you can see shadows on the left of the image being cast through the clouds and dust of the nebula. And on the right image, you can see that that star in the center is actually two stars, not one. It's a binary system. And that's the first time we've been able to properly image that second star. And exoplanets are a big motivation for JWST. This is the spectrum of the atmosphere of Wasp 96b. Wasp 96b is a giant planet outside our solar system, composed mainly of gas. It's a hot Jupiter, so it's kind of like Jupiter, but it's much closer to its host star. And this planet and the planetary system is located 1,120 light years away from Earth. And it orbits its star every 3.4 days, so extremely close. And it has about the same size, but about half the mass of Jupiter. And this is a transmission spectra, so we look at the light being blocked from its host star as it orbits around, and then extract the leftover spectrum to see what the atmosphere of the planet is made of. And we can see here it shows water vapor in the atmosphere, and that old model, so the blue line, doesn't fit very well. So it shows that we are now detecting a lot of things that we didn't previously detect, and we need to develop these new models, and that means new science. So over this time, we've slowly been getting closer and closer in these images. And Objective 4 that we see here, Planetary Systems and the Origin of Life, isn't just about other planetary systems, because we have our own to look at, and that's our solar system, and that's what I'm going to be talking about today. So not many people know that it's going to be used, or JWST is going to be used to look at objects in our own solar system, because most of the press, like today, was about those big astrophysics and cosmology questions deep in the universe. But a lot of the coolest science is going to be in our own solar system. Okay, I'm a little bit biased, but I think it's the coolest. So what in the solar system is JWST going to be looking at? It's going to be able to observe everything from Mars out. So planets, moons, asteroids, Kuiper Belt objects, comets. And that's more difficult than it sounds for a telescope that was primarily designed to look at distant objects like those galaxies that we saw. Because galaxies and stars, they are very distant, and that means that they're dim, but they're also stationary on the night sky. And everything in the solar system in comparison is very bright and also very fast moving. So engineers had to overcome these obstacles to make solar system science possible. So they had to make sure that JWST could move, so it can track these objects moving quickly. And it also had to make sure that it doesn't break when it looks at something bright. So for planets and rings, we're going to be looking at Mars all the way through to Neptune. There are restrictions on the maximum amount of brightness that we can put into the telescope. So we have to make sure that we use the right instruments, and instrument modes have to be chosen depending on what's being viewed and how bright it is. And for the planets, we can look at their atmospheres, their clouds, hazes, circulation patterns, composition. We can see what they're made of. We can see what the weather is like and why it's like that. And we'll come back to these in a little bit more detail when we look at what's going to happen in the first year of observations. And all of these images here, apart from Mars, are VLT images. And VLT is a very large telescope, which is actually what VLT stands for, Very Large Telescope, that's in Paranal, Chile. So really beautiful things we can do from Earth. And my favorite planets, the ice giants, are the most exciting for me, and probably for everyone, I hope. And we'll come back to them when I talk about my research a little bit. So not just planets, but their moons too. And the moons of the solar system are some of the most interesting bodies in the solar system, because places like Europa and Enceladus, they're cold, but they might have these deep subsurface oceans that may contain life. And also we have moons like Titan, which is the only body in the solar system where there are rivers, lakes, and oceans like on Earth, but instead of them being made of water like they are here, they're made of methane on Titan. And this image here of Titan is from Cassini infrared instrument, and it shows the ability of the infrared to look through the haze and reveal the surface of the planet, of the moon. And again, this is another place where there may also be life, but maybe not as we know it. Then we have asteroids and comets, otherwise known as primitive bodies. And these are of huge scientific interest because they're the leftovers from the formation of the solar system, and they can tell us a lot about the solar system. So asteroids and near-Earth objects like Eros are very faint because they're so small and cold. So they're hard to observe, but JWST has the sensitivity to do this. And they contain answers to some of the biggest questions, and they help solve mysteries of the early solar system and planet formation, and even maybe these bodies brought life to Earth. It's still unknown. Another form of primitive bodies are Kuiper Belt objects, or KBOs, otherwise known as trans-Neptunian objects, or TNOs. Asteroids are mostly in the asteroid belt between Mars and Jupiter, but KBOs are beyond Neptune in the Kuiper Belt. So they're much colder, much further away, so they're even harder to observe than those asteroids. But again, JWST has the sensitivity to be able to look at most of them. And you might think you don't know any Kuiper Belt objects, but Pluto is considered a Kuiper Belt object. And also the largest moon of Neptune, Triton, is also thought to be a captured Kuiper Belt object. So my job now is to support the solar system scientists who will be using JWST in the GTO program. And the GTO program is the Guaranteed Time Observation Program. And these programs are awarded to the science teams that contributed significantly to the design and hardware and software components of JWST or helped plan the observatory's scientific mission. Heidi Hammel is the scientist that was awarded the solar system time, and she is now one of my supervisors, along with Stefanie Milam, who's the JWST deputy project scientist for planetary science. And myself and my colleague Ian work on this. So I work on everything planetary, and Ian works on everything small bodies. So each of these bullet points is a program that has a team of scientists and time on the telescope to look at these targets. And the team of scientists are from many different institutions across the world. And these targets are being looked at in this first year of JWST observation. So they're very important observations. And so my job is to work with those scientists in getting them from data that we get from the telescope all the way through to publishing their science successfully. And we're also both on the moving target and scattered light commissioning teams, which means we helped with getting JWST ready for science. And I'll explain more about that towards the end. And so I'm going to talk about my 7 programs and give you a little insight into what is planned or already being done over this next year. So I'll start with our closest neighbor, Mars. It's one of the fastest objects that JWST can track. It's also one of the brightest because it's so close to us. And we're able to observe when it's at its dimmest, and we can make global maps of Mars like the one shown. And so we can show what it's made of and what the atmosphere is like, and also what the surface is doing. And using NearSpec and NearCam to do this, we're going to be using it 1 or 2 months from now. And this has we might be able to answer some very big questions, like what happened to make the ancient lakes, oceans, and rivers on Mars dry up? What could Mars ever, could it have ever hosted life? And was it in the distant or was it in the recent past? And what causes Martian global sandstorms? So in 2018, there was a global sandstorm where a sandstorm literally covered the entire planet. And that's especially important to understand if humans are to ever visit. This video in the bottom is from The Martian. It's not a scientifically accurate representation of how we could lose Matt Damon, but a Martian sandstorm is dangerous for communications and also for navigation. And so it's important that we understand the precursors of them and why they happen. Jupiter is the largest and also one of the most challenging objects to observe with JWST. It's big, so scientists will have to mosaic multiple images together. They won't just put the whole planet in one shot. And it's also extremely bright. So this mosaicing also helps not to saturate the detectors or make them too bright. And infrared is extremely useful for looking below the clouds and the haze to see into the deeper structure of the atmosphere, like in that top image that I showed previously. And we're using MIRI, so that mid-infrared instrument, to determine the three-dimensional temperature, composition, and aerosol distribution in the Great Red Spot. And these observations have already started. And notice for Jupiter, for the GTO, we're only looking at the Great Red Spot. And that is because there's also another much larger observation campaign called the ERS, or the Early Release Science, which is to be used as a kind of example of all the brilliant things that we can do in the solar system. And they're going to be characterizing Jupiter's cloud layers, winds, composition, temperature structure, and even its auroral activity. And we're going to produce maps of moons, the main ones like Io and Ganymede, and also some of the smaller ones, and also characterize the rings. For Saturn, because there's no big ERS, we are targeting the whole system. And so following the EPIC 2017 conclusion of the Cassini orbiter mission, the goal is to establish a baseline for continuing observations of the planet, satellites, and the rings with all of the instruments. And these observations have already started as well. So NIRCam should be sensitive enough for discovering new moons, if there are any, of Saturn. And NIRSpec is going to take spectra of selected small known moons. And MIRI is going to be used to take spectra of the main rings and also be used to make a mosaic of Saturn's famous North Polar hexagon to try and understand more about it. Now, we're going to be targeting two of the most interesting moons in our solar system with 3 instruments starting later this summer until the end of the year. We're going to take high-resolution observations of the jets emanating from these moons, measuring what they contain. And this will reveal information about the processes acting beneath the moon's thick ice crusts and the potential for habitability of the subsurface oceans. Specifically, do they have these submerged hydrothermal vents like we do on Earth in that picture in the bottom right? Do these or can these host life? We just don't know. It could be possible. And Titan is going to be observed with 3 instruments in autumn of this year. And we want to advance our understanding of Titan's gases, hazes, clouds, and surface composition. This near-infrared color mosaic of the Cassini, from the Cassini spacecraft shows the sun reflecting off Titan's north polar seas, which I always think is really beautiful. And JWST will expand on what Cassini found. So now the only GTOs missing are my favorites, Uranus and Neptune. So I decided to dedicate a whole chapter to them because I can. So what makes an ice giant an ice giant? The size, they're smaller than Jupiter and Saturn, bigger than Earth. The stuff that they're made of, they are hydrogen and helium based, and they have no surface, just like Jupiter and Saturn. They both have rings and moons, and we think they have the same origins, but we're not sure. And when we say ices, we mean heavier, like elements with a higher freezing point than hydrogen and helium. And that is things like methane and water. Methane is the thing that causes both of these planets to be blue, just like the methane in our own atmosphere causes our sky to appear blue to us. And this picture here is a best guess of what's going on underneath what we can see. So we have our cloud layer with methane, ammonia, water, hydrocarbons in it. then the deeper we get, the higher pressures we get and the higher temperatures we get. So we end up with things like a supercritical water ocean, maybe, when we get a little bit denser, and then even denser further, we end up with a solid layer of superionic ice, which is that crazy black ice stuff. And then underneath that, we might have a small rocky core. But we know so little about both of these planets that there are even papers going around where people say that they should be called rock giants, not ice giants. So we really know very little. So we know so little about them because we have only visited them once with Voyager 2 in the late 1980s. So each line on this little graphic that I found shows the path of a spacecraft mission. So all of those lines around Jupiter, Saturn, even Pluto, and Venus, Mercury, they've all had a lot of things happen, whereas there's only one line going around both Uranus and Neptune. It's the same line, and it was from Voyager 2 doing these very fast flybys of Uranus in 1986 and one of Neptune in 1989, and that's it. We haven't been there since. And everything else has to be done by remote sensing, which means we're looking from a distance, and that's what I do and what James Webb does. So I already talked about them both being ice giants, so they have a lot of similarities, but they also have a lot of differences. So both of them are interesting for us to study. So Uranus is kind of known as the weird one, and Neptune is kind of known as the normal one. Uranus is my favorite because it's the weird one. And it's because Uranus has an extreme axial tilt, whereas Neptune has a normal Earth-like axial tilt. That means the angle at which it's rotating. And they both have different amounts of internal heat, which shouldn't be the case. And that means that affects the activity in their atmosphere. So we get a sluggish atmosphere at Uranus, but we get quite an active one, a very active one at Neptune. And Uranus has lots of little satellites, so lots of little moons and rings, whereas Neptune has one large captured satellite, like I talked about with Triton. Yeah, Uranus is kind of the weird one. So we'll start with our typical ice giant first, Neptune. So Neptune is our furthest away one. It's the one that takes 164 Earth years to orbit the sun. And the atmosphere is highly dynamic, some of the most dynamic fast speeds in the solar system that we know of. And this video here is from the flyby of Voyager 2 in 1989. And you can see that big purple thing is actually the great dark spot rotating into and out of view. And on the left, we have some Hubble images that show how dynamic and variable the atmosphere is, even over short timescales of a couple of hours. Then we have Uranus, our weird ice giant, my favorite. And it's closer to us and closer to the sun, obviously, than Neptune, but the atmosphere is colder, which is the opposite of what it should be. And so it's only 84 Earth years orbit around the sun. And that extreme axial tilt is at 98 degrees, which means it is rotating on its side, which no other object in the solar system is doing that. And when Voyager 2 visited, it was at solstice. And that's why in the video, you can only see its poles rotating at us, because that's all that Earth could see. And that's all that Voyager could see at the time. And in 2007, during the equinox, it looks more like this top video where the rings are edge on. And it just looks like a strange sideways planet. So my research uses the Spitzer infrared spectrometer. Spitzer was launched in the same generation of telescopes as Hubble in 2003 and decommissioned in January of 2020. It was in an Earth trailing orbit, so it's following us around the sun. And it was pretty small. Its mirror was less than a meter across, so 0.85 meters. But it had a similar wavelength range to the JWST. It also looks at heat like the JWST does. But Spitzer looks at the mid-infrared and all the way out into the far infrared. But with the infrared spectrometer that I used for my research, we're only looking in the mid-infrared range, the same wavelengths that the mid-infrared instrument on the JWST uses. So why is the mid-infrared useful in particular for these planets? So here's some example images of Uranus from visible through to microwave with other space-based and ground-based telescopes. And we can also apply this science to Neptune as well. They're both similar in that respect. So these different wavelengths are sensitive to different depths in the atmosphere. So on the right, this shows the vertical structure of an ice giant atmosphere. And so we're showing the stratosphere and the troposphere separated by the tropopause. Below the tropopause is the troposphere, and above the tropopause is the stratosphere. And we can see where each of these wavelength bands sense. So visible and near infrared, the blue and purple, like Hubble Space Telescope looks at the cloud tops, so around the tropopause in the upper troposphere. And that's useful for sensing what the clouds are doing and the dynamics and how fast those clouds are traveling to see wind speeds. Whereas microwave will look a bit deeper and look deep into the troposphere, and that's the green arrow. And then the mid-infrared can see a lot more. So the mid-infrared is the red arrow. And we call this the thermal infrared, again, because we're looking at heat. And that looks at the stratosphere and the upper troposphere, which is very useful for sensing where a lot of chemical reactions take place. Convection, which is the lifting of gases, causes methane to be lifted into the stratosphere, so above that tropopause into the stratosphere. And then when it's in the stratosphere, the sun kind of interacts with it, and photons from the sun knock it to pieces. So it's broken down by the sun, or photodissociation. And then once it's broken down, methane is broken down into its constituent parts, then it starts to reform into complex hydrocarbons, chemicals like acetylene, ethane, methylacetylene, and lots of crazy sounding things. And observing these chemicals tells us a lot about the atmosphere. So Spitzer was used to observe both ice giants between 2004 and 2007. Because it's so small, we have a small problem. We can't get any pictures. So those pictures that we saw before, unfortunately, we can't get anything pretty. But these to me have become pretty. It's called a spectrum. So a spectra is where we split the light up like a rainbow, and then we look at how much light there is at each color. And then the little bumps and troughs tell us what it's made of, and it can also tell us other things as well. So we have to treat these planets kind of like stars. We're just treating them like point sources. We can't actually see them close up. And these are two example spectra from 2007 equinox of Uranus and from the 2005 image of 2005 data of Neptune. So as I said, the bumps and troughs show us what the atmosphere is made of, what temperature it is, and also how it changes at different depths. It can even tell us a little bit about weather and circulation patterns. And we can see the main features of methane and those complex hydrocarbons. That's all of the funny letters and numbers. And the overall shape of the spectrum is governed by hydrogen and helium, those main constituents of the two planets. And comparing the two together, we see the same general trend, so that they're similar. They have similar features, they have similar chemicals, that's why they're both ice giants. But we see the effect of Uranus having a lower temperature in the fact that it makes the data noisier, and also it's harder to read and extract information from it. There's a lot more bumps and wiggles that shouldn't be there, and that's the noise. And these spectra are global averages, which means that they're from lots of different times that have been averaged together. And that's important because those different times show us different sides of the planet, because as time passes, they rotate. And my PhD investigation split up those different longitudes to see if anything is changing between them. So the plot on the left shows the different longitudes that the observations come from for Uranus in 2007. And we see we have a nice spread all across the 360 degrees of rotation of the planet. So do we see a difference between each longitude? Yes, we do. You can see a consistent variation. So the right plot shows the difference in radiance for the entire range of data for those 4 different longitudes. So longitude 3 in green shows much dimmer atmosphere or emission, whereas longitude 4 in purple shows a brighter emission consistently through all of the data. And to look closer, we can look at each chemical species in the spectrum individually, and these are shown by the bands in different places shown in the plot. So each species contributes to a different height in the atmosphere. So this plot shows the contribution for each pressure level in the atmosphere, so each height. And everything, remember, everything above the tropopause is the stratosphere, and everything below it is the troposphere. So an example, methane here, when we follow it down and look at where it contributes in the atmosphere, we can see it contributes in the stratosphere, whereas with hydrogen, helium, and also CH3D, which is a different type of methane, they contribute deeper down in the troposphere. And so what we do with this information is we plot the variation of each species as Uranus rotates and see if there's a change over that rotation, over those 360 degrees. And we can see that those tropospheric species, so the hydrogen, helium, and the CH3D, don't have any change. They stay on that middle line, 0% change. Whereas the methane, CH4 in black, has a lot of variation, considerable variation, and that's the stratospheric species. So if we look at even more species, we see that same variation in all of the stratospheric hydrocarbons at varying levels. So we know we have some kind of longitudinal variation in the stratosphere only. But we don't know whether it's a variation in temperature or gas abundances or what physical process or feature is causing it. And there are different ways we can find clues as to what's going on. One way to find clues is to get some spatial resolution somehow to see what's going on, which we'll talk about in a second with this Keck image. And another way, which is what the main part of my PhD was on, is modeling the variation. So we use a software called NEMESIS to do something called optimal estimation retrievals of the data. That's shown in the left plot. So that's the model or the retrieval versus the data. So we try and get them as close as possible. And we modeled each longitude separately and found as a result that it's realistic that it could be a change in temperature only. So the right plot shows the changes in temperature needed for that variation that we were seeing. And we only need around a 3-degree difference in temperature necessary to cause the changes we see in that spectrum, which isn't a lot and means that it is possible that it's just 3 degrees of change. So let's go back to some images. These were extremely lucky images from the NERC-2 on the Keck telescope in Hawaii, which is a really big telescope, around 8 to 10 meters in diameter. And these were taken 4 days before the Spitzer data. And they're in the near infrared. So remember, we're sensing kind of the pressures around the tropopause. And we have 2 opposite hemispheres in this data. So the left is centered at around 80 degrees longitude, and the right are centered at around 230 degrees longitude. And the top and bottom are just 2 different filters. And we see that we have one active side and one dormant side of the planet. Around 80 degrees, we have a lot more activity, a lot more. For Uranus, we have a lot more activity than we have on the other side. And that active side corresponds with the coolest stratospheric emission, which, remember, a 3-degree cooling could cause what's happening. So it could be that these features are causing this cooling and making it so that our whole spectrum is cooler. And that could make sense if the activity is bringing up some cold gases from below. And we also have data in the mid-infrared from the VLT in Chile, again, a very big telescope. And it shows, apparent stratospheric spatial variation in these images as well. But these are from 2009, so it might not be this exact thing that's happening, but maybe something that happened similarly in 2007. And do we see the same thing at Neptune? Strangely, we don't. We see a less than 2% variation across the same species in 2005. And before, we mentioned that Neptune is highly dynamic, highly variable. So this is the absolute opposite of what we thought. We thought we would see more variation. But one hypothesis is that it's too dynamic. One feature that stands out isn't going to happen when the hemispheres look similar and have this much activity. But all we can do is kind of guess at this stage. We won't get any real answers to what and why this is until JWST. So there are major advancements from Spitzer. Again, the size, 6.5 meters is a big step up from Spitzer's 0.8 meters. And just to put it into context, the Spitzer mirror is the same size as the JWST secondary mirror. And the secondary mirror is the one that's on the end of the boom that focuses the light into the instruments. So that's how big JWST is compared to Spitzer. And the instruments are also more advanced. They're more sensitive and have better spectral coverage. We have better spatial resolution and better spectral resolution as well. What about Earth ground-based? So I mentioned that most of them are huge. 10 meters in diameter is normal. And 3 of these images here are from the VLT in Paranal in Chile. That's in the background there. You can see those telescopes together. And then one of the images is from Keck, which is in Hawaii. And we can see how detailed we can see with each of these telescopes, even in the mid-infrared, which are those 2 images that are in the orange. And mid-infrared is very difficult from the ground because of atmospheric absorption. Between 5 and 30 microns, which is where the mid-infrared is, this is where all of the really interesting data is for temperature and composition of atmospheres. And we can get good spatial resolution. These huge mirror sizes help, but because of this absorption, especially from water, we have poor spectral resolution, which means we only really get one wavelength band at a time. And that's because we only have these very small spectral windows that you can see where like one's at around 9 microns and then there's another one at 10 microns. You only really get these small windows where you can look through the atmosphere. So we've seen we currently frequently have to choose between finding out what something is made of and what it looks like. So an example here is with Uranus. We either have to choose information or image. Information, like with Spitzer, where we don't have any images, but we get a lot of spectral information, or with the ground-based instruments where we can't get those spectra, but we can get quite nice images. But JWST, we can get both using something called an IFU. This is an integrated field unit. So each pixel in an image also has an associated spectrum. And that means we have information and image at the same time. And this forms something called an image cube because it has 3 dimensions of information. And each pixel inside that image or cube is called a spaxel rather than a pixel because it's a spectra and a pixel, which I think is a really cute name. And that's extremely exciting for scientists involved, especially when it comes to the ice giants. So what are the plans for the JWST GTO? Well, we have a fair amount of allocated time, enough to map 360 degrees of both planets at multiple longitudes. And so we have 3 longitudes of Uranus being observed in late summer of this year, and 2 longitudes of Neptune being observed this time next year. And both will be observed in both the mid-infrared and the near-infrared. Out of our 4 instruments aboard the telescope, we'll be using MIRI and NIRSPEC. But why specifically these 2 instruments and not the others? This is the JWST imaging and spectroscopic capabilities across the whole spectral range for all of the instruments, from 0.6 microns in the near infrared all the way through to 28.5 microns in the mid infrared. And here are the instruments that were being used for the ice giant GTO. And it's this that we're interested in. Again, it's the IFUs. We really want to get the image cubes at all the wavelengths that we can. These image cubes are going to be game-changing. I'll explain a little bit more in a moment. A little bit about the instrument. So NIRSpec was developed by ESA, the European Space Agency. So the NIRSpec IFU provides a spectra from 0.6 to 5.3 microns, and it's mostly being used to look for evidence of the magnetosphere at Uranus and Neptune, and look for a chemical called H3+ that is formed in the very high atmosphere and is a sign of auroral activity like the northern lights on Earth. And the plot on the right shows the planetary spectra of all four giant planets, Jupiter, Saturn, Uranus, Neptune, compared to the saturation limits of NIRSpec. So saturation limits means how much light the instrument can handle before it stops working. And everything below the black lines can be observed with NIRSpec IFU. So all four giant planets are observable in this instrument, so it's very exciting. Then we have MIRI. MIRI is my favorite instrument because I'm a mid-infrared scientist, but also because it's a UK-led instrument. The University of Leicester, where I did my undergrad and PhD, were the structural and engineering lead on this instrument, which is really cool. And it has similar wavelengths to Spitzer, but it has better spectral and spatial resolution. Specifically, the medium resolution spectrometer, or the MRS, it contains 4 IFUs. So we see the size of all 4 in the bottom plot compared to the size that Uranus and Neptune will appear from JWST. And it looks like the MRS was built just for observing both ice giants. It really does. They both fit perfectly in the field of view. And the right plot again shows the MRS filter saturation limits. That's the red curves this time. And we have to be careful with Jupiter and Saturn with the mid-infrared. But Uranus and Neptune are observable over the entire spectral range because, remember, they're much colder than and further away than Jupiter and Saturn. So before launch, it's vital to know the capabilities of MIRI for these planets. So we have done some simulations for what the data will look like when we get it. And that allows us to plan ahead for actual data to analyze the actual data. So what we did was we generated synthetic data cubes in the resolution and wavelength range of the MIRI MRS. So the right image here is part of an example data cube of Uranus. So it's just a little snapshot of the cube. So each pixel in that image has a spectrum of a similar resolution to the snippet shown at the above. So it's really, really high resolution in both spatially and also spectrally. So with these instruments at these wavelengths, there are the main science goals of the GTO. We still know so little about both planets, so they're still pretty broad compared to the other planets. We're going to generate spatially resolved global spectroscopic maps of both planets. These will reveal contrasts in atmospheric temperatures and chemical traces. We're going to do a full chemical inventory and investigate climate, seasons, and weather. And we'll also investigate how each layer of the atmosphere influences one another. And then the results for Neptune and Uranus will be compared to try and understand a little bit more about the differences between the two planets. Something exciting, recently I got awarded Hubble time to look at both ice giants at around the same time as JWST. So this is an example of how Hubble and JWST will work together in the future. And it's exciting because we get extra wavelengths. Hubble will let us see into the visible. And that's exciting because dark spots at both planets are only visible at blue wavelengths. So we wouldn't be able to see them in the JWST data. So we need Hubble to be able to do that. Also, with those IFUs, or those image cubes, we get a lot of information, a lot more than we did with Spitzer, but we sacrifice a little bit of detail compared to the near-infrared camera images that we can get from Hubble. And yeah, we can get much better detail from Hubble to identify those small storm features that might be influencing the temperatures and the variations. And this really will enhance the science that JWST is going to be able to do. So the last section, I thought I would update you on where the telescope is now. And I'll start with a look at where it's been. It's been a long time, and I haven't been here the whole time, but I've been here for a fair bit. And so work on the project began over 30 years ago, again, just before Hubble's launch, so before I was born. And it was first discussed as a successor to Hubble Space Telescope in 1989, and it was called the Next Generation Space Telescope, or NGST. And construction of the first elements, like the mirrors and instruments, started back in 2004. And I really enjoy this right image here. It's a very early concept design for the Next Generation Space Telescope from scientists at Goddard, where I'm currently based. And it shows a lot of similarities to the JWST that we know today, shown in the left image, including our large deployable mirror, the open telescope design with the boom, with the secondary mirror at the end of the boom, and that large multi-layer sun shield. They even figured out that they needed to put it at the L2 Lagrangian point all the way back in 1995-96. And it's been a bumpy ride. There have been a lot of delays. It's been known as the just waiting space telescope a lot. But all of the delays were worth it now, because after its trip down to the ESA spaceport in French Guiana last year, I'm sure most of you saw the launch on Christmas Day. Everything went extremely smoothly. So smoothly, in fact, that there is enough propellant for a lifetime of over 20 years. And that means that the propellant won't be a factor in the retirement of the telescope. It needs that propellant to be able to move to target new to look at new targets. So every time it looks at a different star, it needs to move a little bit. That uses some fuel. So we need fuel to be able to work the telescope, but we will have over 20 years worth of it. And the telescope is so big, it has to be stuffed into the nose cone to be able to fit. And you've probably heard the term commissioning a lot in the last 6 months, and launch was the first stage of commissioning. And there are 3 stages. So the first phase was the spacecraft commissioning, which meant launch, and then its deployment and the beginning of cooling to operating temperatures. And the second phase was the telescope commissioning, which was aligning the mirrors and the other optics. And the third phase was the scientific instrument commissioning, which is the calibration and characterization of all 4 of those instruments. And all of that takes about 6 months, took about 6 months, past tense, because we just finished this process yesterday, which is very, very, very exciting. I'm going to be saying the word exciting a lot today. And the hardest and most nerve-wracking part was phase 1. As it traveled to L2, it unfolded from its launch configuration. Remember, it had to be stuffed into that telescope cone, into the rocket cone. And it had to unfold into its launch configuration to actually become a telescope. And the JWST had the most single point failures of any mission ever sent to space ever before. And by comparison, a usual Mars lander, one of the most complex things we've done as humanity, apart from JWST, will have about 100 single point failures, whereas JWST had 344 single point failures. So any one of those things went wrong and it was not a mission. But now it's fine. We only have 49 left, and they're the normal kind that is in any mission, like propulsion systems, and they remain throughout the lifetime of the telescope. So tick, phase 1, done, success. The second phase was telescope commissioning or mirror alignment. It's 18 individual hexagonal mirror segments. Remember, they all work individually. They needed to work together as a single high precision optical surface and focus that light on each of the 4 instruments perfectly. And this was also a success. And we saw the release of these images and the comparison of MIRI to one of Spitzer's other instruments, the IRAC instrument. And you can see the difference in those images. You can really see the advantage of having such a huge mirror. And this image here on the right shows all 4 of the instruments with their light successfully focused, so in that last phase. And instrument commissioning can begin now that that's happened. And I'm involved in a team that did a part of this process of commissioning. So each instrument mode has been tested, calibrated, verified, and signed off as ready for science operations. And in my team, we did 2 things that are important for solar system observations. So we did moving target tracking. So we're observing objects in the solar system that require us moving the telescope as we're looking at it. And so all objects in the solar system require this. And so the observatory has to change its pointing direction relative to the background guide stars during the observation, and harder than it sounds. And so we tested this capability by observing asteroids at different apparent speeds using each instrument. And then I was also part of the scattered light testing team, the same team. And what happens if a bright source gets in the way of an observation? Will anything break? Can all the functions still work? Will all the instruments still produce images? Even if, like, how close can we get to a bright source before we have to be like, okay, that's too bright? And that was all a success. So what's next for JWST? Well, science. Science. So science has already started, actually. And the first solar system GTO targets are already being observed, Saturn moons and Jupiter specifically. And Uranus is being observed in August, and we'll have to wait until June 2023 for Neptune. But it'll be worth the wait. And GTO will keep us busy for the next year during cycle 1, and then scientists will propose even more science for cycle 2 and beyond. So it's going to be a long relationship with JWST. And we're also looking even further ahead into the next 10 years. So the decadal survey says Uranus orbiter and probe. So a Uranus orbiter and probe was prioritized by the recently released planetary decadal survey. The NSF, or the National Science Foundation in the US, they recommended to NASA that the priority for planetary science for the next 10 years should be to launch a flagship level mission to Uranus. And this is the kind of timeline we're looking at, but it's just an estimate. We should start development in 2024, which gives us 7 years until a launch window appears. We want to be able to make the most of a Jupiter gravity assist available in 2031. And then we have a 13-year journey arriving at the system in 2044. I'll be 54 years old. And the arrival depends on what rocket we use. So if we use the new super heavy rockets that are just being tested and sorted out now, we could get there up to 4 years faster. So it's definitely a good time to be an ice giant scientist or to get into ice giant science. And I have something very exciting to show you that only came out about an hour ago. I didn't think I was going to be able to show you, but the thing that it was in was published, so it's no longer embargoed. So this is the first JWST image of a planet in our solar system. So this is Jupiter, and these are some of the images that we got when we were doing scattered light commissioning. So these are imaged using the NIRCam instrument in 2 filters at different wavelengths. So on the left we have 2.12 microns, and on the right we have 3.23 microns. This is Jupiter with some of its moons and even its ring. I'll point some of these things out. So you can see Thebe, Europa, Metis, so 3 moons that you can see. And you can also see that amazing ring, and also the Great Red Spot shown there, the GRS. And then you can also see, which I think is the coolest thing, Europa casts a shadow onto the disk of the planet. So you can see that shadow just next to the Great Red Spot, which is really amazing. And this is so amazing because this is just accidental imagery of the planet using an instrument when we were just testing scattered light. It wasn't even optimized, or we weren't looking for anything. It was just, it's got to be in the field of view so we can test some scattered light information. And that just makes it even more amazing because it's basically an amazing accident, on a purposeful accident. So I'll leave you with some links you can visit for more information, and you can follow me on Twitter for updates on the ice giants and also JWST. And I thought I would leave you with that beautiful image of JWST just after launch as it disappears on its way to L2. Thank you. I'm looking forward to your questions.